Hey, all right, students. I'm glad somebody's asking about this one. This could be a tough one. There's a top loop and a bottom loop and a big loop. And as I was trying to say in the lecture, don't do all three loops. Either do the top or the bottom, and but not all of them. Okay. Um, and then there's a node. The currents come together. Well, here they kind of show the currents, so we'll follow their labeling. But the node here at E would do kind of the same thing. So we need to do one of these nodes. So we need to do like the top loop and the bottom loop and a node to get our three independent equations. We know that there's going to be three currents. You can see that along this top branch it would all be I1. There's no other place for it to go. Along this bottom one, they're showing number 3. So they're showing number 3 over here, but it would be number 3 all the way around. In fact, I kind of like to just kind of help myself and say, okay, that all the way around is current number 3. And then this one, they're saying all the way around is current number 1. And then across the middle and actually going in reverse of this battery, which I'm not real sure why the author labels it that way. Oh, no, I'm sorry. I don't know why I was thinking reverse. That's going that way. Yeah, that's the push. And it's the biggest battery, 48. Some can go backwards, but according to this, nothing's going backwards. Going backwards would charge a battery. Going forward would drain a battery. So the direction of the current, its natural path, would be in the direction it wants to push, which is positive coming out of the battery. That's what it wants to do because of the chemical reaction. But a bigger, stronger battery could force it the other way. That's what you probably do every evening or night when you plug in your cell phone. You are plugging into a bigger voltage supply and shoving the current the opposite way and recharging that battery so it'll be ready for the next day. All right, well, I thought I'd go with green in the currents here so they kind of stand out, given that the author already used black and blue and red here. But this is a pretty long problem, so I better jump on this. Here's what the question says. What does the question say here? I lost it. It says number 38. It says find the current flowing in the circuit. All right, so let's find each of these three currents, I1, I2, and I3. It looks like they label a lot of resistors. Let me start with, I think, maybe the easiest one, and that's this node here at A. But that says the current's flowing into the node, so that would be current number 3 is going in, equals what comes out. And so that would be number 1 and number 2. And just to illustrate, as I did in the lecture, number 1 would be coming in and number 2. So if you were looking at node E, you would say 1 plus 2 equals what comes out, number 3. And that's exactly the same statement. So that's not a new piece of information. As I said in the lecture, kind of focus on how many unknowns do you have, which this would be 3 because we have the current in each branch and there's 3 branches. And then look how many loops you have, small loops, 1, 2 small loops, and know that that's how many independent equations you can get from your loops. So you can do the 2 small ones, which is usually what I recommend, and although sometimes doing a big one and like one of the small ones is nice. Just don't do all 3 and think you have 3 independent equations. That's the part that I was saying. If you did all 3 of these and you went to solve it, you would finish the problem and get something like, 5 equals 5. Because you didn't do anything wrong. It's just you don't have enough information to come up with the answer of what the current is. So that's how I know I'm going to have 2 equations from the loops, and then I need 1 from the node. That's going to give my 3 independent equations. All right, so with that in mind, maybe I'll go ahead and I'll just do this top loop, and I'll start at A and go A to B. And so as I add up around this loop, the resistance is 5 and the current is I1. So I'm going to go 5I1. And since I'm going with the current, it would be a negative sign. Then as I go B to C, that's an increase of 24. I know it's an increase because I go from small bar to big bar. That's what we mean in a battery, and it's 24 volts. I go C to D. That was going with the current, so it's a minus. And it is a 0.1 I1. And, of course, then this right here, resistor number 5, has a 20, so it's 20 ohms, and it's still got a current of I1, and it's still with the current. In fact, as you begin to gain more experience with that, you'd probably recognize that all three of these are going to have the same, and you could have just added them together to begin with because they're in series and get 25.1, and that's ultimately what I'm going to do is add the three of those together and get 25.1. Okay, but then as I get to E and I go from E to, must be an L, from E to L, I'm going against current number 2. So I'm going uphill, so there's a plus against the current, and it looks like it's 40I2. And again, I'm going against the current, so it's another plus, and it looks like it's a half a ohm for the internal resistance, and we're still talking about current number 2. Then I get to another battery here. This is a 48-volt battery, and I go from big to small, so this is minus 48 equals 0. And maybe I should come back here and label this first one. Let me simplify this one before I label it. As I said, we could put all the I1s together. And if I did that, that would be a negative 25.1 I1. We could also put all the I2s together. There should be 2 of them here, yeah. So there'd be plus 40.5 I2. Okay. And then we can put our numbers together, and it looks like a plus 24 with a negative 48 leaves me with a negative 24, and that equals 0. Okay. In fact, maybe I'll do one more. Now, let's call that number 2. All right. So that's equation number 2. So I've got this one and that one. All right. Let me go ahead then and do, let's say, the bottom loop. Why not? And maybe I'll start at A and go across this middle branch and around the lower branch here. All right. So as I go from A to K, I go plus 48, right? It's a battery, little to small, so it's plus, and it's 48. Then I go with the current and with the current. So I'll just put those two together, 40.5 I2, and I'm going with the current as I'm walking around. Gets me to E. And as I mentioned back on equation 1, why don't I save myself a little bit of work and just realize that this is definitely going to be a resistor for number 3, and then this will be a resistor for current 3, and this will be a resistor for current 3. So all of these are eventually going to be added together. So why don't I just do that now and call it a 78.25. And that would be I3. And as we go from E all the way to A, we go with the current every single time. So it'd be a minus. And then we've got these 2 batteries. As we would go this way, we would go down, so negative 36. And here we would go up, so plus 6. And that would return where we started. All right, and I guess I'll simplify this one too, but there's not too much to simplify because I already put the 2 resistor ones together. Let me just write it as minus 40.5 I2 and minus 78.25 I3. So those were the 2 currents involved, the number 2 and number 3. But then I got these 3 batteries. So it looks like these 2 right here make a negative 30. And then with the plus 48 makes a plus 18. Is that true? Let's see. 48 minus 30, 18. Yeah. All right. And so let me call that equation number 3. Put a little mark there. All right, so I have these 3 equations and then 3 unknowns. All right, let me put the schematic off to the side because now I'm done with the physics. Now I need to do the math. And this is the one that in the lecture I said maybe the best thing to do is to use, say, this one right here, I3, and put it right here. So you now will no longer have an I3 in this third equation. And then I2 doesn't have an I3 in it. So then you just have what left would be two equations, two unknowns here. But I'm going to take this as an opportunity to show you some nice, powerful features of your calculator. It's often referred to as a Cramer's rule or matrices. Maybe you've come across it. It's kind of introduced early on for students, but it is really a nice, powerful tool. So as long as I'm just doing an extra video solution, let me show you this tool. You can kind of see it best if you put all the variables on one side and the constants on the other. So let me do this. Let me write this as negative I1, negative I2, positive I3 equals 0. That would be this first equation with all the variables on the right-hand side. Now, let me do the same thing here. So this is a negative 25.1 I1. This is a plus 40.5 I2. There is no I3, so I'll just put a 0 and then move the 24 to the other side. And then this one, which I guess I forgot to make it an equation by setting it equal to 0. I guess I'd have a negative 40.5 and a negative 78 and a quarter I3. There is no I1. And so let me just write this equation, again, with all the variables on the left-hand side. And so let me move that to the other side. Now, here's why this can be useful. In just an algebra class, you would think of this as a system of equations, three unknowns. But written like a matrix, it's a single equation. And we can solve a single equation really easy with our calculator, although we have to know how to put a matrix into our calculator, and that's kind of what I thought I'd take advantage of showing you. Now, for me to do this, I guess I got to remind you a little bit about matrices. But if I write the coefficient right here, negative 1, and 1, and then the variables I1, I2, and I3, this, when you take this matrix and multiply by this matrix, you take everything in this row, corresponding with everything in this column. So you'd go that negative times I1, that negative times I2, and then this positive times I3, and you would get it equal to 0. And so this first equation, written as a first line in our matrix, is what that represents. The same thing here, you can write this as a negative 25.1, a positive 40.5, and a 0, then equals 24. And so again, just to kind of remind you of matrix multiplication, it says as you multiply everything across this row and then this column, so that would be this one right here, you have the negative 25.1 times I1, the positive 40.5 times I2, the 0 times I3 would equal the 24. And then the last one would be, of course, 0 times I1, negative 40.5 times I2, negative 78 and a quarter I3, then equals negative 18. What's, of course, really nice, like I said about this, is what was 3 equations and 3 unknowns now is one matrix equation, which you might say is still 3 unknowns. But in a minute, I'm going to grab this calculator and I'm going to put this, what the calculator will perceive as one matrix equation, and it will solve that one matrix equation for me. In other words, if I could do some manipulation so that this matrix looks like this. Looks like a 1, 0, 0, 0, 1, 0, 0, 0, 1, often called the identity matrix, because as you can see, if we manipulate the left-hand side, but using the same rules of mathematics for the right-hand side, if we get something that looked like this, see, this would just say 1 times I1, and then 0 times I2, and 0 times I3. That means this side of the equation is just I1, and so I1 would be equal to A. And so that's the beauty. What we're going to do is let our computer do all the work. Reduced row echelon form is what it's called. Okay? And we'll just let the calculator do all the algebra for me. And technically this is referred to as linear algebra, but you might recognize it more as Cramer's rules of matrices when you were learning a little bit about matrices and determinants. All right, so I'm going to go to my calculator. I'm using the TI-84. Here's the matrix menu. And what I'm going to do is set myself up by creating a matrix. And so I'm going to go to Edit Matrix A. And the first thing it's going to ask me is, what size do I want? And so I'm going to call it a 3 by 4 because I'm going to enter in 3 rows and 4 columns. It would be the matrix here, which are these 3 columns. This is kind of assumed in the calculator, and then this is the 4. So if I enter -1, enter, -1, enter, 1, enter, and 0, enter, that would be the first row. Then a -25.1, enter, 40.5, enter, 0, enter, 24, enter. Okay. Then go 0, enter, -40.5, enter, and -78.25, enter. And finally, the last one, -18, enter. And then I'll just quit. So I've entered that. Now let's go back to that matrix menu. I guess if you wanted to see it, I could just, hit matrix A. See, it says matrix A, and say, hey, show it to me. And so here it is, 1, -1, 1, 0. And maybe I can just confirm I typed it in right. -25.1, 40.5, 0, and then that's 24. Okay, going back. 0, -40.5, -78.7. Okay, so that's my matrix A. I'll just say quit. Okay. Oops, I keep typing matrix A. Okay, so I'm good. Now, what, like I said, is nice is the calculator can do all this mathematical manipulation for me. It's called a reduced row echelon form. So if I go to my matrix and say, what kind of math do you want to do on your matrix, I can go RREF. RREF of, and I'll go to matrix A. And so that's the fancy mathematical operation. It would be the same as on your calculator hitting the sign of something. It's just an operation, the sine or a cosine or a log. But I want the RREF of matrix A. So if I hit enter, you'll see it changed the matrix. It did a lot of what we call reduced row echelon form. It multiplied rows by columns, did a lot of math in there, and eventually got this side. It figured out what did it need to do to this side and to get to here, which would be the same as here. And so what this is telling me then is I1 is equal to a negative 0.344. I2 is 0.379. And I3 is 0.0339. Okay, so there it is, where the calculator did all the work. Although, first time doing it, it might seem like a lot of work putting in your matrix, and especially if you're not familiar with matrix and matrix operations. So maybe the algebra would have been better for me to go through. Maybe it would have been a little easier. But the calculator can be really powerful. And so I know that if we were doing this a little deeper and long-term, I would go through a little video here and say, look, take advantage of our matrices. They're really, really nice, and especially when we get to a lot of other, well, we could have done it back when we did torque. Torque's another good place to do matrices, but we didn't do that in Physics 110. All right, well, with that, before I say we're done, it might be nice just to confirm all this, starting with noticing that current number 1 is a negative. And so what that really is saying here is that this bigger battery here, and for that matter, this is bigger also, although it's been reduced down by this much by 6. So this is like equivalent of a 30. But both of these really are blasting the... no. Wait, I3 was positive, right? Okay, so this goes here, and then it goes against this battery. So we're charging up that battery. But I wanted to point out then it would be going this way and against this battery. So that current is going the other way, okay? But we can confirm that our math is true. Really, that is when you add 1 and 2, you get 3. And 3 is a small number, and I guess that makes sense. This is trying to go through, and this one's pushing this way, this one's pushing back. This is pushing of equivalent of a 30. This is 48 with some loss of energy. So eventually this one wins, but not by much. And so I think if we add these two, the 0.379 and the negative 0.344, yeah, we're looking within rounding at the same number. And so really this is saying that barely any goes down along this loop. And what does go around this loop, most of it goes around this loop, and it's going opposite to the way we fixated it. Now, again, maybe just for educational reasons, we should probably just kind of check this. You might do something like this, that, okay, going from A to E, so from A to K to L to E, there would be a change of voltage. And we could probably figure that out really well, because there would be an increase, say, of 48, but we're going with the current, so there would be a decrease. And if I put those two together, 40.5 times the current of number 2, 0.379, we would see that the voltage change, delta V, from A to E would be the 32.65. And so again, it went up, but then down because of the loss of energy going through these resistors. So what that would say is if this is the increase, then going back this direction or back across the top, we should decrease by the same 32. Or put another way, if we went from A to E along this bottom path, we should increase by that 32. And so let me give that a try. Let me do this bottom one, because as I go along the bottom one, I would be going against these 3 resistors. and I would go up here but down here. So in terms of the batteries, I would have a net of 30. Go up 36 and then down 6. So remember, I'm going from A to E. So down 6 and up 36. So there's a change of 30 from the two batteries. And then I'm going against the current, so plus, and I can just add these together again, the 78.25 times this very small amount of current, which is 0.0339, and that should be that 32.65. So good. It is confirming that going from A to E along the center branch or A to E along the bottom branch is still an increase of the 32.65. And then we can do from A to E along the top one too. Let's start with the battery. From A to E right there, the B to the D, that, or B to the C, excuse me, is the increase of 24. Okay. And of course, now my picture and my thinking needs to be adjusted because I originally wrote it with the idea that the current was going in the direction that they indicated, but their indication is actually opposite of what it should be. It's actually, current's going actually the other way. So now that I know that, I will think of myself going against the current. So in other words, I have a 24 and then plus Ohm's law, where I'll take each resistor. So 25.1 when I add those three together, times the currents in number one. And in this case, it's the magnitude of the current because I've already taken care of the negative by saying I'm going against the current. I'm thinking of it as the real current. So this should be also that 32.65, okay? Other than rounding, it's right there. So feeling pretty confident about that answer after now checking out using the principles of conservation of charge, since 1 and 2 added to 3, and then the principle conservation of energy, that is A to E, was an increase of 32.65, whether I went the middle branch, the bottom branch, or the top branch. So quite sure I did that right. All right. Hope that was helpful.